Look at a modern manufacturing line. A precision robotic arm grabs a mechanical component and seamlessly slots it into place. That machine is part of a control system. Its entire purpose is to manage a physical process so that a specific targeted result is produced every single time. But despite appearing intelligent, these machines do not actually understand the physical world. They rely entirely on a rigid translation pipeline to bridge the gap between their environment and their internal digital logic. Control systems are categorized based on how they handle this gap. Some operate blindly, executing instructions regardless of external changes, while others observe their environment and adapt. A system's ability to adapt to changing conditions relies entirely on its underlying architecture, specifically whether it is built using an open-loop or a closed-loop design. This diagram outlines the basic control system model. It starts at the blue input node, representing a target value entering as data. That data moves to the process stage, where a controller evaluates the input and chooses a physical action. The decision is executed, resulting in the output block, the physical change produced by the machine. But crucially, the physical result is sensed and fed back into the system to be checked against the original input. The presence or absence of this single feedback loop is the structural dividing line between simple execution and true machine adaptation. Let's look at the baseline diagram on the left, the open-loop system. It does not measure the real-world result of its actions, relying strictly on preset instructions. Notice the text at the bottom. There is no feedback path from the output back to the input. A basic timer-based toaster operates exactly like this. The user provides the input by setting the Browning dial or timer. The process begins. The heating element runs for that fixed number of minutes, and finally, the output occurs when the bread pops up. The weakness of this architecture becomes obvious if the starting conditions vary. If you put frozen bread into the toaster, the machine runs the exact same process, unaware that the bread needs more heat. Because there is no mechanism to correct mistakes, open-loop systems fail when physical conditions change unexpectedly. Compare that to the closed-loop system on the right. This architecture continuously measures the physical result via the feedback path and adjusts itself accordingly. Achieving this feedback loop requires a specific chain of hardware components. It starts with sensors. These are the physical devices that detect quantities like temperature, light, pressure, or speed in the real world. Next are transducers. They convert one form of physical energy or signal into a usable format, usually translating a physical change into an electrical signal. That data goes to the controller, the hardware or software brain of the operation. It compares the initial input against the new feedback, makes decisions, and sends out command signals. Those commands reach the actuators. This is the muscle of the system, receiving control signals to produce a physical response, like spinning a motor. This continuous hardware pipeline allows a closed-loop machine to constantly translate a chaotic physical environment into actionable digital data. We can see this pipeline at work in a standard central heating system. The input is your target temperature. The sensor is the thermometer reading the air around it. The controller processes the thermostat logic. If needed, it triggers the actuator, a switch turning on the boiler. The resulting warmth in the room acts as the continuous feedback. Now, consider traffic lights, which can be built using either architecture. A simple fixed timer traffic light operates strictly on an open loop. It cycles from green to red based on a clock, regardless of how many cars are actually waiting. But if engineers add vehicle detectors under the asphalt, they introduce sensors. The junction is upgraded to a closed-loop system, adapting the light timing to the real flow of traffic. Injecting sensor data and feedback structurally transforms a static mechanism into an adaptable, responsive system. Hardware alone cannot make decisions. The controller requires ordered rules to operate. This chart breaks down the control algorithm, which is the specific logic used by the controller to determine its next action. In Step 1, it reads data from the sensors. In Step 2, it compares that current state against the desired state. Moving to Step 3, the controller uses its decision rules to determine what needs to be done, and in Step 4, it sends those signals to the actuators. Finally, Step 5 ensures the cycle repeats continuously, so the closed-loop system remains accurate over time. For a thermostat, the rule is simple. If the measured temperature is below the target, switch the heater on. Otherwise, switch it off. The control algorithm serves as the deterministic heartbeat, driving the autonomous physical corrections. Comparing these architectures reveals key trade-offs. Closed-loop systems provide higher accuracy by correcting errors through feedback, but this requires greater complexity and higher costs. Conversely, open-loop systems suffer lower accuracy when conditions change, but prioritize simplicity. They are much cheaper to build and operate. The choice between these two approaches depends on the specific requirements of the application. Closed-loop architecture is not automatically better. If a task is simple, predictable, and requires low cost, open-loop is the superior engineering design choice.